Welcome back to lecture 3, part 3 on evolvable hardware. And for this final lecture, I want to just talk about another project done at York called the ARE project, the ARE project, which stands for Autonomous Robot Evolution. So this is an ongoing project that's going on at York. So what were the aims of the ARE project? What are the aims of the ARE project? So it's to demonstrate the first hybridized co-evolution of robots in material. What does that mean? It means that we want to build real robots, so that's the immaterial bit, and also we want to build a simulator of those robots, so that we want to hybridize between real robots and simulated robots. And what we want evolution to do is take maybe a real robot and a simulated robot as parents to create the next generation of robots. So that's where the hybridization comes in. And we want to build the environments, so both in simulation and in the real world, to perform experiments on these robots. One of the other things that's important when we're doing this type of system, when we're doing this hybridized system, is to characterize the trade-off curve. So what I mean by that is we've got two ends of a spectrum in some respects. So we've got evolution can keep going almost forever to make something fit for purpose, but it takes a long time. And the other end of the curve would be to try and minimize the amount of time we give evolution to produce new robots. And so what we need to do is to try and find the optimal for that in our evolution. And of course, having done that, what we want to do is actually perform experiments, so both in simulation and on real robots, to see what results we get and how evolution performs. And then finally, the aim of the project, the third aim of the project, is to demonstrate that the efficacy of this methodology in a mock real world scenario. So one of the scenarios we're looking at is a nuclear cleanup scenario. So building a replica miniaturized cave of what a nuclear area might look like, with pipes on the floor and bricks and things like that. And can we get robots to evolve and operate in those sorts of environments? So that's the idea of the project. They're the main aims of the project. This is a excuse me, a cartoon which shows some of the main features of our environment. So here in this pyramid, we've actually got a robot fabricator. So this, and we'll see in details what that actually is in a few minutes. So this is where robots will be made, will be fabricated. And then we've got a nursery area. So where the new robots will come out and they'll train and they'll learn new skills, like, for example, object avoidance, or maybe how to pick something up. Just very basic skills that you might learn when you're young, if you like. And then when we're happy that the robots are mature, they can go out into the arena. So they can go out into a more complex arena where they would do tasks. And as I said, one of those tasks might be something like a nuclear cave cleanup. So that's kind of the basic structure from the hardware side of things. And of course, because we're 3D printing robots, then we might recycle bits of plastic and things like that for the next generation of robots if we've got ones which aren't very good. So that's a bit of an overview at the top level. I said we will see more details in a few minutes. So the goals of the ARE project are to advance, in fact, the state of the art of evolutionary computing. So actually this idea of evolving both morphologies, so that's body plan, and the controllers, is quite new. Very few people have tried to do this before. Most people using evolution on robots look at evolving controllers, but they've already got a designed body. In this case, we want to do both. And so the chances are we'll need new evolutionary methods to actually be able to do this properly. And of course, what we do need is when they come up with a morphology, it needs to be in a representation which we can then build the robot. And in this case, in this project, build the robot means 3D print it. Okay, so use 3D printing to print the robot. And we'll see some examples of it near the end. And of course, once we've got the representation, we then need the infrastructure to allow us to go from effectively genotype to phenotype to build the robot, to manufacture the robot. So we need this environment and this infrastructure to do that. In addition to that, remember I said it was hybridized. So actually on the simulation side of the thing, so rather than the hardware, we're going to need a virtual environment, which will map the real environment. So as it says here, it will contain high fidelity models of the robots and the environment and the outside world. And one of the things to do that, so there's a very famous phrase in robotics called the reality gap. And what that really means is you do something in simulation, you think you've got a model of the robot and the world. You then build that robot, you translate the controller, if you like, to a real robot, and you find it doesn't perform the same as in simulation. And it's because the simulator isn't perfect and it doesn't map everything in the real world. So one of the things we'd like to do in this project is once we've got a robot and we've got its model, can we tune the model to make it more real, make it more represent the real robots? We want to, within the robot, we're going to produce an autonomous management system. So we want these things to be completely autonomous, both the physical and the simulated things. So we're going to build an ecosystem manager, which will allow all of those processes to go on autonomously, including evolution, including testing for survivability, testing for manufacturability, and making a decision whether a particular genome is going to go to simulation or whether it's going to go to the real robot to be manufactured. So all of those things are going to be done within this ecosystem manager, within this autonomous management system. And then, of course, we've got to build a physical environment for our experiments. So quite a lot to do. It's quite a big project. So here's an example at the highest level. We'll see in a minute a bit lower level of our system. So we've got our ecosystem manager at the top here, which is basically managing everything. So it's managing the evolutionary algorithms, it's managing where robots are built, whether in real physically built or within the environment. And you can see the left-hand branch here is maybe what we're more used to. So we get an evolutionary algorithm, we get a member of a population which has got a genotype, which goes down to this virtual environment. So a robot is created in the virtual environment, it performs some tasks, it gets a fitness function, and we go around the evolutionary loop. And at some point, the genomes of good ones will be passed back to the ecosystem manager. On the right-hand side, we've got an evolutionary algorithm, which may or may not be exactly the same as the one for the virtual environment, which then produces a genotype. But now this actually goes to the robot fabricator to build, to 3D print and construct the robot. And then it goes into a real environment for training and hopefully into the final arena for doing some real tasks. And again, the fitness is passed back. So you can see the two branches are similar. It's the physical environment part here is slightly more complex than the virtual environment. So let's look at this in more detail. So what we've got again on the left-hand side is the virtual environment, and on the right-hand side is the physical environment. So what we've got here is we've got a loop which builds virtual robots which are run in a virtual arena down here on the left-hand side. Okay, let me go back a bit. So what we want to do, because ultimately we want to also build them, we've also got an extra test, which is to do with the viability, the manufacturability. So can we actually, the robot that evolution has come up with, design that evolution has come up with, can we actually build it? Okay, so when everything's put in a virtual environment, that's not something that's normally looked at. But actually in this environment it is. So the virtual environment is that way. If we look on the right hand side, this is the physical environment. And of course what's happening down here is from the blueprint that we've got that comes down from the ecosystem manager and the evolutionary algorithm, then is to be put into the robot factory to be built. And so there are various issues to do with that. So actually are components put in the right place? Can we actually physically build them within the environment, so without human intervention? So there are extra tests that we wouldn't normally see within an evolutionary algorithm that we need to include in here. And so if it doesn't pass the viability, then typically it might just get junked. and it certainly wouldn't be built at that point there. Okay, so this is a more detailed view of what the environment looks like. Okay, so let's have a look at a few examples of where we are so far. We're 2 years into a 4-year project, so we're halfway through. So here's some examples of robots in the simulator. So we use VREP for the simulator for the robots. And what you'll see here is we've got a robot body or skeleton in green. So in there, and in this case here, it's a fairly simple one. This is just the white here. The big white cube is the brain. So every robot has a brain. So that's kind of given. Evolution can't choose that, but that's a given thing. And the brain fits into the skeleton. And we'll see in a minute in the video how that works. And then the robot has a number of organs, what we call organs. So it might have wheels. So we can see that one's got 2, this one's got 2 as well. So these are clipped onto the skeleton. You can see there's a pictorial version here of how that might work. And then we've got sensor organs. And again, the sensor organs are clipped onto the skeleton. So what evolution does is it creates a skeleton of which the brain can fit into. And then it starts placing organs around this skeleton, and then it chooses what those organs can be. So they can be wheels, they can be sensors, and the sensor organ in reality has a number of sensors it can choose. And also it has limbs, so it has kind of an arm or a leg, which you can choose, and it could fit on to these clips. So here's a couple of designs that work, that operate. And this shows a lot more design. So remember, evolution is going to produce a large population of these robots. So you can see here that they've all got a brain. So the little white cube in the middle of all of them. And then they've got a skeleton of various levels of complexity. So some of them are rather simple, like this one here. Some of them are really rather complex, and probably we would never build these. And then around them, they've got a number of organs, as I said. So this here is a limb on this one here. So you can see that there's a very wide variation in the body plans, as we'd expect, because it's evolution that's creating these, so we've had no input into these. So the question then is, do we want to build them? Do we actually think they're viable? So that, as I said, there's a manufacturability test to show that. Okay, so let me first of all show you an example of a simulated robot in VREP. So here we are. We've got a skeleton, we've got 2 wheels, we've got 2 sensors, and this at the back here is a limb, like an arm or a leg. And you can see that this robot is being guided, and the limb is changing as it's going around the system. And the idea is this was the home base that it's meant to find. So it's using the sensors to avoid objects and get to there. So this is quite interesting because it's a relatively unusual structure. Normally things maybe just have wheels, but with this limb as well, it makes it slightly more difficult to control. So the controller was evolved as well as the robot body. So that's a nice example of a slightly unusual robot that evolution has come up with, but we managed to evolve a controller that made it work. Okay, so let me talk about the RoboFab now. So the thing that actually creating the robots. So what we've got here, before I start the video, let me just go through this. So we've got a robot arm that's doing a lot of the work. Over here, we've got a 3D printer, and you'll see already there's a skeleton in red here that's been printed. So that's already been printed. And over here, we've got what we call an organ bank. And on the organ bank, we've got a brain, which is that green printed box there. And we've got some other organs that we'll see here. So we're at a process where evolution has come up with a robot. The robot has been printed. So the skeleton has been printed here. And what now is we have to construct the robot. We have to put the robot together. And again, we want to do this autonomously. So just the other thing to note here is up here, we've got an electromagnet. At the bottom of the brain module here, we've actually got 4 metal plates. So what we'll see is the first thing that happens is the robot will take the brain, put it into the skeleton, and then put that upside down on here. And this allows us then to construct wheels below the surface of this, etc. So let me start the video so you can see what's happening. So as I said, the skeleton's been printed. So the robot arm now is coming over to pick up the brain, so this rather larger organ here on the left-hand side. From the organ bank. And then what it does then is it clips it in. You can see some red things on the side here. So these are clips, there's one on each side, and they clip in to a standard clip that every skeleton has. There we go. You could hear the click maybe there. It then picks that up off the 3D bed. The electromagnet system up here has moved into the right position. As I said, what it does now is it connects the 4 metal discs on the bottom of the brain, which you just see there. You can see them there. Connects to the electromagnet there. There we go. So it's now ready to have all the organs put on. That's somebody just checking that they're pushing a wire in that just popped out. So what it does now is it's going to go back over here to the organ bank and pick up wheels and pick up sensors and clip them onto predefined points on the skeleton that evolution had created during the process. So what you'll see is, as well as that, this is moving around into the appropriate position to allow the arm to click on an organ. So you can see here, you can maybe start to visualize here why we need a manufacturability, a viability test. Because if the arm can't actually connect something on here because there's something obscuring it, then that would no longer be a viable robot. So this at the moment has picked up a wheel organ. You can see that it's going to connect it onto the skeleton. There we go, that wire's dropped out again. And now it goes back to get a second wheel organ to connect on. And we'll probably see this move again into the right position. So that's it, it's got a second wheel organ now. It's going to connect it to the, you can see that moves slightly, so it's in the right position for the wheel organ to be connected. Good, so that's got both wheels on. What it's now going to do is going to go down and start picking up a sensor organ. This might be an infrared sensor or a mixture of sensors that the robot then uses to detect objects. You can see these are a bit smaller, but they've still got a common clip where the things all clip together. You may have noticed that the robot swiveled around to be in the right position for a sensor to be connected. That's that one on with the skeleton. I think it fits one more sensor organ. So this particular evolved design, so remember again, this was evolved, has 2 wheels and 2 organs, 2 sensor organs. And again, the robot moves around into the right position. You can now see the sensor organ that we just put on there, and it's now about to fit on the second of those 2 organs. But again, this isn't being done remote control. It's all being, once it's all set up, and the evolution has been done, it's all done autonomously. Good, so there we go. We've got a skeleton, we've got a brain, we've got 2 wheels, organs, and we've got 2 sensor organs. Because now we've got to power all these up. So there's a battery in the brain, and what we need to do is connect up that battery to these other active elements. So what we've got over here is a series of cables with 2 jack plugs on each end, a jack plug on each end. So what this now does is the robot arm goes over and picks up one end of a cable. There we go, you'll see that picked up. It then picks up the other end of a cable. Okay, ready to now go and connect up effectively the power to the organs. You'll see it first of all puts the cable through some strange movements. You can see the jack there. You can just about see the jack there. That's first of all going into the organ. We're a bit worried about whether it's going to fit or not, but I think it does. There we go. So that's effectively the power end. The battery is, and then the other end of the organ. You see the cable got quite tight, but it just about managed without pulling it out again. It now fits the other jack plug into one of the organs. We've changed the design slightly since this video, where the cables are actually part of the organ, so there's less chance of the cables being pulled out or tangled through the construction process, but basically it's the same. So that goes into one of the organs. There we go. So that organ now is powered through the brain with the battery and that thing. And what would then happen in the rest of the process is these other cables you can see here would connect up the other organs so that they're all powered in the system. So that allows us now to, that produces, so evolution has created a body plan and an inertial controller. What this system does is it actually creates that. So it actually builds it, 3D prints it, and then connects up various organs and connects up those organs to power. And here's an example of that robot just moving around. So you can see it's got 2 wheels, 2 organs, it's got the cable on the top, and it's got the brain. So to be fair, it's not fantastic. It doesn't work brilliantly. You can see this wheel is slipping. There was a little help from a friend. It carries on moving. But it shows that actually the whole process does work. And that actually from evolution, we can go all the way through to autonomous printing, autonomous construction with a robot that is practically functional. There are obviously a few problems. And things have moved on quite a lot, in fact, since we took this video. So that's the project. So it's the first ever attempt to evolve both morphology, body plan, and brains controllers in robots. So it's a fundamental experimental tool, in fact, to enable evolutionary researchers and people that want to look at novel robots to actually consider those sort of things. And actually, ultimately, what we want to do is investigate robots in remote and hostile environments where they can actually adapt and evolve based around those environments. So here's a couple of papers that we've produced over the last couple of years, which may be of more interest, gives you a lot more detail of some of the aspects of the project. So this is the end of lecture 3, and it's the end of the 3 lectures on evolvable hardware. And so what I hope I've done is give you a bit of an idea of how evolvable hardware links to the previous lectures, where you've looked at more software-based methods for evolution. And you've seen how it can be applied into different areas. So things like digital and analog systems, electronics, autonomous adaptation of hardware, and of robots. And so, you know, evolvable hardware isn't good for everything. And actually humans are pretty good at designing many things. But it does have advantages in certain areas and certain applications, which we think are very, really useful things to explore. So just finally, to finish off these 3 lectures, there's a couple of really good books here. I shouldn't plug them too much, should I? But they're nice books. If you want to actually investigate the area more, they're in the library. And if you actually want to investigate evolvable hardware more, then these books give you a nice overview of what's going on. So I hope you've enjoyed these lectures, and I think the next series of lectures are on swarm systems and things like that. So hopefully you'll enjoy those for now. Okay, thank you very much.